Okay, so I'm hearing that the last problem on section 7.4 was hard.
No, well, it's 19 and 20 because they were like.
Oh, are they related? Okay,
Yeah,
so 19 and 20?
They were continuations.
Okay, 19 and 20. The numbers 1, 2, 3, 4, and 5 are written on, this is on page, just so that Sierra knows what's going on, page 317, problems 19 and 20. The numbers 1, 2, 3, 4, and 5 are written on slips of paper, and 2 are drawn at random at a time without replacement. Find the probabilities in exercises 19 and 20. So, find the probability that the sum of the numbers is 19. Okay, well, I can think of a couple of ways to do this. I'm sorry, is it 19? Is 9. Okay, so sum is 9, and you have the numbers. This pen is probably not ideal for videotaping. Mine doesn't show up so well. Let's try a darker one. Okay, you have the numbers 1, 2, 3, 4, and 5, and you're going to draw 2 of them. Now, how many combinations of these guys actually adds up to a 5, to a 9? Just one. The only one that adds up to 9 is 4 and 5, right? This would be a way harder problem if it was asking which ones add up to 6, right? Because lots of combinations do, but only one of this does this. Now, I'm saying the word combination because I think that would be one way to solve this. I mean, one way to say is, how many combinations are there of, I always forget how this notation in this book worked. Did it say 5 things drawn 2 at a time? I mean, if I pull 2 out of there, there's only so many and the order isn't mattering. 5 and 4 is the same thing as 4 and 5. I would do it this way. Now let's see, combinations. Is that the one where it's n? Did we do this? Wait a minute. I'm thinking, or am I thinking of quantitative reasoning? Ah, crap. Okay. Hold on. We haven't learned that yet in this class. Sorry, they just did probability in that class, and they're not learning it quite as detailed as you guys are. But yes, they just finished this.
Like the union rule probability and the intersection rule.
Yeah, okay, so you're just doing this with union rule. Okay, let me think about this for a minute. Then I would say probably, oh, wait a minute, somebody did this problem, and she didn't like it. Was it MJ? MJ, how did you do this problem not liking it?
I just did I think it's like the union rule or something like that. It was like the P and then E, it's the union F, and then...
You drew a picture, and you did it with a union rule.
Yeah, but I also said...
When you drew a picture, like, did you make yourself a table with all the possibilities? Is that what you mean? Yeah, that would be, okay, first case, again, who else did this problem using a table or something like that? That would be my first thought. Make myself a list of all the ways it could go. Like, you could get a 1 and then a 2, a 1 and then a 3, a 1 and then a 4, a 1 and then a 5, a 2 and a 1, a 2 and a 3, a 2 and a 4, and a 2 and a 5. I mean, there aren't that many. A 3 and a 1, a 3 and a 2, you can't get a 3 and a 3, 3 and 4, 3 and 5, 4 and 1, 4 and 2, 4 and 3, and 4 and 5, or 5 and 1, 5 and 2, 5 and 3, or 5 and 4. Those are the only ways you could draw it. It's not that many. This would be a pain in the butt way to solve this problem if there were 200 numbers in there, right? But for a small-ish number, there's nothing wrong with solving it like this, and in that, you can see that there are 1, 2, 3, 4, 5, 4. There are 20 ways this could go, and only one of them adds to 9. Okay? So that would be one way of doing it, yes.
But then, do you have to count them out, like, what I did, how it worked for me, I had to cross off any, like, duplicates.
Well,
Because technically then it would be 2 out of 20, which would be 1 out of 10. Because...
What is the answer to that in the book?
One out of 10.
1 out of 10?
Because whenever you cross out, like, you can't...
Oh, they crossed out the 2. Okay, so they were saying...
Or they simplified, because then it would be 2 over 20.
Oh, wait, there are 2. Wait a minute. It's 5 and 4 and 4 and 5. It is 2 out of 10, 2 out of 20, which is 1 out of 10. Sorry. I was going to say, it should have worked the same both ways. Okay, so yes. Okay, so either way would have been fine.
I just wrote down complete your random answer and thought I got it right for a second.
Sorry.
I'm mad.
Sorry. Wrote down a complete... I got to grade your stuff more carefully. All right, so yes. There were 20 ways it could happen, and 2 of them were right. All right, now... Was it MJ did it trying to do it with union rules and stuff like that?
Yeah, and then I gave both.
Okay,
Just, like,
because you're
mapped
right.
it out,
Here's the
and
deal. You could do it as the probability that your first one is a 4, and, like first is 4, and second is 5, plus the probability the first is 5, and second is 4.
See, I never got past that.
But that would be, but you could get that far. I mean, and then it's a union rule problem.
Right,
In fact,
I got that part,
Yeah.
but I never got past it.
So, yeah, so we could do that. I mean, probability, the first is 4. Let's see if this works. Let me see if I can do this without making a mistake. So the probability of the first one is going to be a 4. Well, we have 5 is going to be, that is 1/5, right? And then, because these are two independent events, right? What you got on the second ticket doesn't have anything to do with what you got on the first one, right? So the next one is you got a 5. Well, there's only 4 tickets left in there, right? So it is 1/4, right? So if you've pulled out a ticket, now there's only 4 left in there. What's the probability that one of those is the 5? It's 1/4. Plus, and then, okay, this is going to be times. Then the probability of this, first is a 5. We got 5 tickets in there. What are the odds of when you pull is number 5? And then what is the odds of the second one? Because you're not replacing. That's 1/4. Oh, so it did work. 1/20th plus 1/20th equals 2/20ths equals 1/10. So it did work both ways. But I think this was harder.
I'm confused how, like, you got the 1/5 and 1/4.
Okay, okay, so when I pull the first ticket, the first slip out, the probability is 1/5 that it's going to be a 4, right? Now there's only 4 tickets left. What is the probability the second thing I pull out is a 5? Well, there's only 4 tickets left. One of them is a 5, right? So it's a 1/4 there. So this is a harder way to think about it, to be honest. I would go ahead and just do it. I would say this is the more... This would be a fine strategy if this was a very large table here, right? You couldn't really write out all 200 possibilities or something like that. All right, let's keep going on this one because this is an interesting one. Number B, the sum of the numbers is 5 or less. Okay, now, here's the deal. Sum is 5 or less. That starts becoming a very difficult problem to solve using union rules. I mean, let's go over here and kind of see what we can do to articulate that. 4, 5, 5, 4. So, we need to find all the combinations we could have drawn that would lead us to thinking we have a sum of 5 or less. Just looking across on here, here's a 5, here's a 5, here's a 5, and here's a 5. And in fact, it's any of these. Right? So, fairly easily I could count that up and say that this is 8 out of 20, which is 4/10. Wait a minute, am I doing this right? Which is 2/5. Is that right? Is that what the back of the book said for this one? 2/5? Okay. For problem 19b. Is that right? Okay. So, again, here the little table made this kind of simple. Now, could we do this with union rules? Sure. But it is going to be a trick. See, what we're going to have to do then is say, okay, so what is the problem? How would we even write it? How far over this way can I go and see her and Lisa can still see it? We're good. Okay. So, this is going to be a big one. How do we express this here? So, it would be the probability that the first number you draw is a 1, and second is 2 or 3 or 4. Okay? Because those are the, right? Plus the probability that this first is a 2, and second is 1 or 3. Those are the combinations that work, right? Or plus the probability that the first is a 3 and the second is 1 or 2. And the probability that the first is a 4 and second is a 1. Because that's the only combination that works there. Do you see how all of a sudden this becomes a big... Don't get me wrong, this will all work out to 2/5, just like the other one did. Because it's going to be the probability that the first is a 1, which is 1/5, times the probability that the second is a 2, 3, or 4. Well, there's 4 cards left, a 2, a 3, a 4, and a 5, so that's 3/4. Plus the probability that the first is a 2, and the second is, okay, there's 4 cards left, and we want either the 1 or the 3, so that's 2/4. Plus the probability that the first is a 3, which is 1/5, and the second is a 2 or a 3. Well, there's 4 cards left, we need either the 2 or the 1, so that's 2/4. Plus the probability the first is a 4, which is, well, there's 5 cards, we only want one of them. And the second is a 1, well, there's 4 cards left, and we only want one of them. If we add all this up, let's see, this is out of 20. So I made it have a common denominator there. This is 3 plus 2 plus 2 plus 1 out of 20, which is 4 and 4 is 8, 8/20ths, which is divided by 4 is 2/5. Holy crap, even I wasn't expecting it to actually work that time. The point is, though, does this look fun? No, I mean, it could be done, it's a union rule thing, but making the table is often the right strategy. But it can always be written out. It's just that it gets complicated. You can see how that even gets to be the case. Now that we have seen how awful these can get, clearly we don't want to write out a union rule for part C. Clearly for part C, where it's getting to be really complicated. Okay, look, the first number is 2 or the sum is 6. I'll just use my blue marker here to do this. The first number is 2, which would mean we're talking about these possibilities, or the sum is 6. Let's see, that would be this one, there's none over here, and this one. So out of the 20 possibilities, 1, 2, 3, 4, 5, 6 work.
5 and 1. Oh, is that already 1?
Oh, 5 and 1. I didn't count this one. You're right. Sorry. 1, 2, 3, 4, 5, 6, 7. So it's 7/20ths for the part C. Again, we can do this with union rules and stuff like that, but it would start getting to be pretty damn complicated, right? All right, number 20. Both numbers are even. All right, sticking with my table there that I've made too big of a mess with. I don't have any other really good colors. Let's just try green here. Got a bunch of markers in my pocket. Both numbers are even. Now we're beginning to see there won't be any of these guys. It could be this one. It could be this one. Well, that's all the only ones, right? There's only 2 ways they can both be even because there's only 2 even numbers in there. Either 4 or 2 and 2 and 4. So it's 2 out of 20 or 1/10. All right, and you can see now the pattern, right? I don't think we need to go through every single one of these guys, do we? Oh. Yep, I mean, all we would be doing is just making more and more of these guys. So here's the deal. I think on 19 and 20, the main thing was recognizing when it was time to just punt over to make the table. Okay? Rather than trying to do this all by hand with the equations. Okay, but this actually makes a really good segue to something I do want to talk to you about in the new material. In the new material, which we're going to be moving into section 7.5, we're learning about another kind of way of expressing probability, which is conditional probability. But before we do that, I mean, a lot of these conditional probability is going to be these kind of probabilities when something is given, like you have a piece of information that is given to you. What is the probability that you won the Mega Ball lottery last night, given that you got the first 3 numbers right? Okay, if they tell you, somebody couldn't remember what the numbers were, but they're pretty sure the first 3 were 2, 6, and 7, and you're like, those are the numbers I played. Now there's a much, right? The probability you won the lottery last night is tiny. The probability you won the lottery last night, if you know you got the first 3 numbers right, is a whole lot higher, right? given the information that you've got something there and there, you can know a lot more. Yes, sir. Luke.
I actually have a question.
Yeah.
This is unrelated.
Yeah.
If you get like 4 out of the however many numbers, do you get like?
I don't know how it
small
works.
amount?
On principle, I don't play the lottery. Yeah, you do win it. You do win it if you have certain numbers. I can't remember how they all work. I have lottery on the brain right now because my in-laws are camping in Arkansas or someplace that doesn't sell Mega Ball or whatever one that's so big right now. Mega Millions or whatever. There's one of the lotteries right now that's right around $1 billion.
Powerball? Or
I forget.
One combined around?
Yeah, something like
We
that.
talked about it last
Yeah, I talked about it. Anyway, so they've been calling us from their campsite, telling us to go buy lottery tickets from the gas station at the end of the street. And I'm like, I've never bought lottery tickets in my life. I don't know crap about this. So anyway. All right, anyway. But before we actually do this, let's talk about these kind of diagrams. If you look at like page 326, page 327, you start seeing some diagrams here that can be kind of useful here. I want to show you these little diagrams. Once you actually look at those little diagrams on 326 and 327, you won't be shocked to be finding out that those things are called tree diagrams. And because they kind of look a little bit like trees. And so we're on page 326 and 327. And I don't know, just because before we even know how to solve problems involving conditional probability, I think it makes more, here's the deal. They teach you formulas for conditional probability and then tell you about these trees. I think it makes more sense to do it the other way around. Let's talk about the trees first. Okay? So look at problem 7, example 7 on page 327. It says, the Environmental Protection Agency is considering inspecting 6 plants for environmental compliance. 3 in Chicago, 2 in LA, and 1 in New York. Due to a lack of inspectors, they decide to inspect 2 plants selected at random, 1 each month, and one this month, 1 next month, with each plant equally likely to be selected, but no plant selected twice. What is probability that 1 Chicago plant and 1 LA plant are selected? Okay, that's a complicated problem, but we can make it with a tree diagram to start helping us understand what's going on. So what they're saying here is we're kind of mapping out the different ways this could go. See, they could go first to a plant in Chicago, or they could go first to a plant in LA, or they could go first to a plant in New York. Then they could go to another plant, right? That's the first month. Here, let's even write that down. This is the first month. They could go to one of those 3. Or then, the next month, they could go someplace to Chicago, they could go to LA, or they could go to New York. If they went to LA first, they could go to Chicago next, then LA, or then to New York. And if they're in New York, they could go to Chicago, they could go to LA, or they could go to New York. See how we've made a chart that explains the possibilities.
The last one you don't need to right?
What? Well, because one of them only has, one of these probabilities is 0, right? If there's only 1 plant in New York, they can't go to New York, then New York, right?
Yeah.
So when we would actually start attaching probabilities to this, one of these paths is not possible, right? Well, let's start attaching some possibilities here. Okay, so of the 6 plants that they are looking at, and let's actually write some of this information down. There are 6 plants that they are inspecting. 3 are in Chicago, 2 are in LA, and 1 is in New York. So that first plant that they go, there is a 3 out of 6 possibility, or 1/2, that it's in Chicago. There's a 2 out of 6, or 1/3 probability that it's in LA, or there is a 1 out of 6 possibility that it's in New York. All right, now, once they've already gone to 1 place in Chicago, so now there's only 5 plants left to inspect. 2 of those are in Chicago, so there's a 2/5 probability that if been to Chicago, 2 of the remaining 5 are in Chicago. If you know you've already been to Chicago, so that's off the list, of the 5 remaining plants, 2 are in LA. If you know you've already been to Chicago, of the 5 remaining plants, 1 is in New York. If you know you've been to LA, 3 of the remaining 5 plants are in Chicago, 1 of the remaining 5 plants is in LA, and 1 of the remaining 5 plants is in New York. If you know you've already been to New York, 3 of the remaining 5 are in Chicago, 2 of the remaining 5 are in LA, and none of the remaining 5 are in New York. Notice, by the way, that on each branch of this tree, I don't know what the right word is, each node of this tree, all the probabilities need to add up to 1. Whatever happens here, these things need to add up to 1. These things add up to 1. These things add up to 1. Whatever happened here, it adds up to 1. But from this tree diagram, we can start figuring out all kinds of things. For example, what is the probability we're going to go to Chicago, first Chicago, second Chicago? It's going to be 1/2, and then we're going to multiply it by this branch. 1/2 times 2/5. See, here's the deal. The actual probability of this is 1/2 times 2/5. It's each of the paths we go down. 1/2 times 2/5, which is going to be 2/10. 1/2 times 2/5 is 2/10. 1/2 times 1/5 is 1/10. 1/3 times 3/5 equals 3/15 equals 1/5. 1/3 times 1/5 equals 1/15. 1/3 times 1/5 equals 1/15. Now, any combination on here we can figure out. What is the probability it happened? 1/6 times 3/15 equals 3/30 equals 1/10. 1/6 times 2/15 equals 2/30 equals 1/15. And this one works out to 0. And by the way, if we added up this column, these things will all add up to 1. Because one of those things happened. Chicago, then Chicago. Chicago, then New York. Chicago, then LA. LA, then Chicago. LA, then LA. And one of those possibilities happened. The tree diagram can be a way to figure these things out. But notice how I built this thing. When I built this thing, when I was trying to fill in, okay, these probabilities were easy to think through. We had 6 places to go. 3 of them were Chicago, so 3 out of 6, or 1/2 are Chicago. We built this part, no problem. This took a little more thinking, because what we really meant was, what was the probability we were going to Chicago, given we already had gone to Chicago once? What was the probability that we were going to LA, given that we've already been to Chicago? Right? Notice the word given in here. We actually have a symbol for that. So what is the probability that the second city will be Chicago, and the symbol is a big straight line, given the first city was Chicago? Notice that notation. The big slash and the big vertical stripe there, it's a pipe on the keyboard. You guys know which one's pipe on the keyboard? Yeah. It's a pipe. Pipe's the straight up and down line. It's above the backslash.
I've never known what that was called.
It's called pipe. Yep. Pipe, and then, so it's then given this. So when I came up with this probability of 1/5, what I meant was, for New York, that what was the probability that the second city would be New York, given that the first city was Chicago? Well, we knew that given the first city is Chicago, we've knocked a Chicago off of here now. Now there are only 5 cities left, one of which is New York, where there's 5 plants left. One of which is New York, so the probability is 1/5. Notice that that's different than the probability that the second city would be New York, given that the first city was LA. Well, maybe. Wait, that was also 1/5. Because we also crossed off one LA here. We still had 5 cities and only one of them was New York. So therefore that probability still worked out to 1/5. What was the probability the second city was New York, given the first city was New York? 0. They're only, right? That's how I came up with this number down here. Once we had crossed off one in New York, there were still 5 plants left, but none of them were New York, so this probability was 0. A tree diagram can be an awfully handy way to solve these kinds of problems, where they help you visualize the different paths through the problem. And if you start flipping through the book, you can see these tree diagrams can get pretty darn helpful. Tree diagrams in general are a mental illness of mine. I have to be very careful in my day-to-day life because I tend to like to, left to my own obsessive compulsiveness, I want to figure everything out with a tree. If I did this first and then I want to get this done, or if I want to take care of this, what if I decide to, I'm going to do this and then I'm going to do this? What if I decide to do, well then I could do this and then I could do, and all of a sudden, someone needs to stop me. Right?
It doesn't become like, then you want to make a tree of, well,
yes!
What if I made a tree or I actually just went and did it? And
yes!
it goes down further from there.
I remember making many decision trees in my life and then somebody at some point saying, you know, like, should I stay in school? Should I drop out of school? Should I go get a job and come back to school? If I drop out of school, would I come back? Would I not? You know, I'm trying to figure all these things out. Trying to find, and it's not a healthy way to think about life. Okay? But it's a thing. Anyway. The trouble is, we can do this using equations too. This is called conditional probability. Conditional probability, which is what this section is about, probability. Conditional probability. And conditional probability is these sort of things where when you know something, where you have a piece of information already. And it turns out that there's a fairly straightforward looking formula that I can never remember. But it's on page 323. I've told you before I was a stats major in college. I was a double major stats and meteorology. And I never could memorize that damn thing. And since most of our tests were open book, I either had it marked or I had it written in the back cover or something because I could never remember that damn conditional probability formula. But if you have 2 kinds of events happening, E is one event and F is another. Like, what can we do here? How about, let's use the room. We're using our room. We're going to pick a student at random. E is, student chosen is a girl. And F is wearing glasses. Okay, so we're in this room right now among the students. I'm going to pick somebody at random. Those are 2 different things, right? And I could have the probability that the student is a girl given that the student I'm talking about is wearing glasses. Right? I'm going to pick a student at random, and what if someone tells me, you got a student with glasses, who's wearing glasses, what's the probability that the student is a girl? Well, we could just right now count on our fingers, because there's only 5 of you here, and be like, okay, let's see, so we've got 4 people who are wearing glasses right now, and 2 of them are girls, therefore it's 2 out of 4, or 1/2. Okay? But wait a minute, it turns out there's a formula for that, because often it's not as simple as we can count it on our fingers, sometimes it's something we have to compute, and it's the probability of E and F divided by the probability of F. So in this case, let's make sure it works. So, the probability, let's write this out. This is the probability that the person is a girl and wearing glasses over the probability that the person I picked was wearing glasses. Alright, let's figure this out. How many people in this room are girls who are wearing glasses? 2 out of 5. 2 out of 5 of the people in this class are girls who are wearing glasses. What is the probability that the person I would pick is wearing glasses? Right now, 4 of the 5 students in the classroom are wearing glasses, so it's 4 out of 5. And if we did the simplifying of the math, that is 1/2. So just our idea of counting works too, or this definition of what we meant by conditional probability worked. Okay, I can never remember these conditional probability formulas. I always have to look them up, but that's okay. You'll be able to too if you need to. Your book makes a thing. Oh, hey, let's do more with this here. Could we have done this the other way around? Probability of F given E. Yeah, I mean, we're reversing this around. What does this mean? This is what is the probability the person is wearing glasses, given that the person is a girl. Okay? So again, we could just do that by counting on our fingers, because there's only 5 of you here. But there's only 3 girls in this room, and 2 of them are wearing glasses, so our answer had better come up to 2/3. But let's check on this here. So this is going to be the probability of F and E divided by the probability of E. So it's the probability that the person is a girl and glasses divided by the probability that it is a girl. And so that would be 2/5, we already counted that one, divided by the probability the person is a girl, that's 3 out of 5. And if you do the math, that works out to 2/3. So it works. Okay. All right. Now your book makes a big deal here about something on page 325. On page 325, they kind of rearranged this equation, pulled one thing over to the other side and called it the product rule of probability. The product rule of probability. But you can see it's the same thing. They just sort of rearranged it. So, like, you know, well, I won't even write it out. But you can see all they did is took that conditional probability rule and rearranged it. And this can be a useful form, but I mean, you would have probably already thought about that. But I do want to write this down for one important reason. I'm going to write down one form of it. How about the probability of E and F equals the probability of F times the probability of E given F. And the reason why I want to show you this is because, here, I'll even put this down here. Let's actually label this guy. This is the product rule. And the reason why I want to show you this is because there's sort of a lingering stench in the room after Wednesday's class. Remember in Wednesday's class, we had that union rule. And that union rule was a useful way of solving the OR type problems. Right? Unions are about OR. Your A or B happens. But these are ANDs. See how we've got an AND here? And we had some problems last time that were ANDs. And we had said the probability of E and F was equal to the probability of E times the probability of F. And we kind of put a star by it because we're like, but it's not quite that simple. And in fact, we even used a powerful vocabulary word at that time, that this is only true if these two events are independent. If the one thing has nothing to do with picking the other thing. I roll this dice over here and I roll this dice over here. Rolling this one has nothing, it doesn't change the odds on this one at all, right? Well, now we have another formula. I mean, look, this one was asking about E and F, and this one's asking about E and F. They're not that damn different. But see, this one's going to work if they're not necessarily independent. For example, on that problem we had with the 3 cities, the choices of your second city weren't independent of the first one. Right? I was a whole lot more likely to pick New York as my second city if I had Chicago as my first city than if I picked New York as my first city. In fact, there was no chance of picking New York as my second city if I had already picked it for my first city, right? They're not independent. Lots of things aren't necessarily independent. This is the form of the equation you use if the two events are not independent. If the second one has something to do if event E and event F are in some way related. Remember the other day we used an example of what was the probability Malia is wearing a coat today? And it is less than 20 degrees. Those things are not independent. You're a whole lot more likely to be wearing the coat if it's cold than if it's warm, right? Those are not unrelated things. But here's the deal. Sometimes it's hard, especially for students, to think through, are things independent or not? And it looks like a trap here that you are looking at two different things and saying, well, wait a minute, how do I know which formula to use if I'm not sure? And I'm going to tell you the answer. When in doubt, use this one. If you're not sure if the two events are independent, use this one. And here's why. This term right here, P, probability of E given F, is equal to P given E if E and F are independent. That's kind of what independent means, is knowing the other thing didn't help. If the probability, what was the, here, let's use a better example. The day that we were talking about, like, we're going to draw a card, it's going to be an ace of spade, and we're going to roll the dice and get a 6. Rolling a 6 has nothing to do with the damn card you drew. Those two things are completely independent. The probability of getting a 6, given I drew an ace, is the same thing as the probability of getting a 6. The ace has nothing to do with it, right? So that can be a thing in your favor. If you don't know if the two events are independent or not, use this formula, because this term, once you do this math, is going to work out to be the same thing as this thing. You're not hurting a damn thing using this formula.
Okay, so
It just won't work.
it comes out to the same
It will work out to the same answer. If you actually do the problem and you're not sure what to do, so you use this formula that's got a probability of F, and this one had a probability of E, that would have been easier, but you're not sure you're independent, go ahead and use this one. When you plug this one into your conditional probability formula and all that kind of stuff, the number you get here will be this damn number. Doesn't hurt any damn thing. It just won't work. But you didn't get it wrong then. Okay? So if you're sure they're independent, go ahead and use that one over there in blue. But if you're not sure, try this. They're not different formulas. The one we had before is kind of a special case. It's the special case of when the two events are independent. That's a pretty slick thing. Let's do an example of some more problems here. Hey, by the way, that business of that rule that I just gave you about how this, with this big long arrow here, probability of E given F is equal to the probability of E if they're independent. That's what they're doing there on page 329 in those blue boxes. Alright. I always like problems that involve decks of cards. Let's look at this problem that's about a deck of cards on page 328. Two cards are drawn from a standard deck, one after another with no replacement. The word with no replacement is important because that means that the second card depends somewhat on what the first card was. I can't draw the ace of spades twice. Probability of ace of spades the first time I drew is 1 over 52, but the second time I draw, it's going to depend on whether I got the ace of spades the first time or not. If I got the ace of spades the first time, then the probability of getting it the second time is 0. There's no ace of spades left. If I didn't get the ace of spades the first time, then the probability is 1 out of 51, because there's one card that's right and there's 51 cards left. Without replacement is often a clue to you that this is a not independent thing. Alright, so A, find the probability that the first card is a heart and the second card is red. And they said let's start by doing this one using a tree diagram. That's fine. First card is a heart and second card is a red, right? Okay. So there's basically two ways this could go when I draw my first card. My first card could be a heart, or it could be not a heart. Okay. What's the odds my first card is a heart?
1/4.
1/4, right? There's 1/4 of the cards in a standard deck are a heart. And 3/4 of the cards in a standard deck is not a heart. And then the second card you're going to draw, is that how the questions work? Probability that the second card is red. So this was our first card. And now we're going to draw another one. And it's either red or black.
No, wait, did it say it was doing this without replacement?
Yeah.
Okay.
So we're going to have to do that here yet too. This is red, and this is black. Those are the 4 ways this can play out, right? Heart, then red, heart, then black. Not a heart and red, not a heart, and then black. Okay. If we know that we've drawn a heart, the first card we've pulled out is a heart. There are 51 cards left. How many of them are red? One red card is already missing.
13.
No, 25, right? Because the hearts and the diamonds are left. Yeah. So hearts and diamonds are left. There's 26 hearts and diamonds, but we've already pulled one heart out. Right? So 25 out of 51 of the cards left are red. How many cards left are black? Out of the 51 cards that are left, 26 are black. Notice, by the way, that in this node, or whatever the right word is, this adds up to 1. Alright, the first card I pulled was not a heart. There are 51 cards left, of which 26 are red. And of the 51 cards that are left, 25 are black. Now the question then is asking, what is the probability that the first card is a heart and the second card is red? Well, then we're going to go through and multiply this down this path. So it's 1/4 times 25 over 51, which is 25 over 204, which I don't think that simplifies. Yeah?
How do you know the bottom could be, because like it couldn't be diamond, and then it would be 25 out of 51?
Oh my god!
That one we have to split.
Wait a minute. And I just did it the way the book did, but you might be right. Hold on just a second here.
Could we split to red, like as in heart, red as in diamond, and then
Well, wait a minute.
black?
So what was not a heart? Oh my gosh. Did you just find a mistake in the book? I think you just did. Okay, so here's the deal. That doesn't affect this branch of the tree that the problem was actually about, right? But you're right. Because here's the deal. Do you see where he's going here? See, the thing is, there isn't necessarily 26 red cards left. If that first card you pulled was a diamond, there'd be only 25 red cards here. You'd still be in the not a heart branch. You're right, the book is wrong on that one. Let's fix that. I think we need to make a third branch here. I think heart, diamond. Are we in agreement that any of the black, we don't have to build a spade and a clubs, right? The blacks are okay. So there's a 1/4 chance that there is a diamond and a 1/2 chance that it is a black card, right? Alright, then red or black. Red and then black. Oh my god, I can't believe there's a mistake in the book, but I think you are exactly right. Alright, so if we drew a diamond, what is the odds the next card is going to be a red card? It's going to be there's 25 red cards left of the 51 and 26 black cards of the 51. And black, there would be 26 red cards left of 51 and 25 black cards left of 51. Each of the nodes still adds up to 1. But you're right, one possibility through here would have been that they had picked a diamond and then a red card, so that would be a different probability. You're right. That's exciting. I love it when we find mistakes. So anyway, your probability of getting a heart and then a red card is 25 over 204, which is a little over 10%. Okay. Could we have done this using an AND kind of thing? Probability of first is a heart and second is red. Yeah. And in fact, we would have to go back to that product rule. let's see, that makes this thing E and this thing F. So this would be the probability of F, which is second is red, given, I'm sorry, yeah, that's it, given probability first is heart, given second, it's the other way around actually. Probability first, so let's call these things the other way around. Let's call this one F and this one E. Then probability of first is heart, and probability that the second is red, given first is heart. Yeah. You'll notice, by the way, on that product rule of probability, page 325, it also, you can use it either way, right? You could either make this the E and this the F, or this the F and then this the E. So the probability that the first is a heart was 1/4 times the probability the second is red, given the first is a heart. Well, the probability that the second is red, given that the probability, given that the first was a heart, was 25 51st, which also works out to 25 over 204, just like it did before. So we could have done it with this giant tree, or we could have done it using the probability rule. Both are happy, useful ways of solving these kind of problems. Okay, where are we out of time? We're running out of time. All right, so for Monday, where did they do with your assignment? Lesson plan. I wanted to make you guys a small-ish problem. Oh my gosh, did I not write this down? Wait, yes I did. Here's the deal. Again, much like the last homework set. Hey, by the way, make sure you get your homework set ready to give it to me. We're on page 330. And we're doing problems 5 through 15 and 23 to 25 and 33, 35, and 36. Notice that a lot of these problems are in the back of the book.
Are you also going to take our test up too?
Oh yes, please, yeah, just go ahead and put them in the same stack. I'll put them out. Yeah, because they aren't able to take the test yet, I can't. So if anybody wants to get points back, especially if you lost a bunch of points on one big problem, just let me know. And we'll have you guys. But honestly, the grades are pretty darn high. There is an exit ticket. I'll get that to you in just a minute.